Hi students, now I am going to teach a problem on the topic volumetric strain. So before going to the problem, first we have to know what is volumetric strain. So volumetric strain is defined as the ratio of change in volume to the original volume. Okay, so the formula it is given as volumetric strain is equal to change in volume by original volume. Change in volume is denoted by delta V and original volume is denoted by capital V. Okay, now we'll see the problem. A steel flat of 250 mm long and 40 mm by 60 mm uniform section. So a steel flat, okay, a steel flat of 250 mm long, okay, and 40 mm by 60 mm uniform section. That means throughout the length the steel flat is of uniform section, 40 mm by 60 mm only. Okay, is acted upon by a tensile force of 40 kilonewton along its length. So a tensional force is acting along its length. So along its length 250 mm, a tensional force 40 kilonewton is acting, okay, at the top and at the bottom. A compressive force of 300 kilonewton acts along its width. So one more force, compressive force, acts along its width. So with the 60 mm, so in width direction, a compressive force 300 kilonewton is acting in both the faces. Okay. A compressive force of 250 kilonewton acts along its thickness. So one more compressive force acts along its thickness. Okay, that is 40 mm. So 250 kilonewton acting at both the faces. Okay. Assuming Poisson's ratio 0.3 as 0.3 and E is equal to 2 into 10 power 5 Newton per mm square, find the change in dimension and change in volume. Okay, so change in volume only we have to calculate. Change in volume is nothing but delta V. Okay, that one we have to calculate. Okay, so this is the figure. I think you all understand the figure. Okay, so length is 250 mm and cross section 40 mm by 60 mm. Okay, the force acting 40 kilonewton, 300 kilonewton and 250 kilonewton is also given in the figure. Okay, now we'll see problem. So first thing, we are calculating the stress. We all know formula for calculating the stress, load by area. So stress in x direction. Okay, so load in x direction divided by cross section area of x direction. So 250 into 40. Okay, so x direction, so in the figure x direction is this. Okay, so force acting in x direction is 300 kilonewton. So cross sectional area is this. Okay, 40 into 60. Okay, so stress in x direction is equal to 300 into 10 power 3 divided by 250 into 40. Okay, so we will get the stress in x direction as 13 Newton per mm square. So first we are calculating stresses. Okay, first step is stress in x direction. So stress in x direction is equal to load in x direction divided by cross sectional area of x direction. So load acting in x direction. Okay, so two forces. This is x direction. Okay, this is x direction. In x direction 300 kilonewton is acting. Okay, so load in x direction divided by cross sectional area of x direction. So x direction cross sectional area is the length will come and similarly the width will come. Okay, so 250 into 40, so 300 kilonewton. So we are converting into Newton. 300 into 10 power 3 Newton divided by area 250 into 40, we are getting a stress as 13 Newton per mm square compressive. Similarly, stress in y direction is equal to load in y direction divided by cross sectional area in y direction. Okay, so this is the y direction. Okay, so load acting in y direction is 40 kilonewton. Then the cross sectional area will 40 divided 40 into 60 mm. Okay, so this one is 60. Okay, so 40 into 10 power 3 Newton divided by 60 into 40, we will getting the stress in y direction as 16.66 Newton per mm square tensile. The next step is stress in z direction. So load in z direction, load acting in z direction divided by cross sectional area of z direction. Okay, So Z direction is given. Okay, so load acting in Z direction is 250 kilonewton. Okay, so 250 acting in this plane. Okay, this one. So the length of the steel flat will come, and similarly the thickness will come 60 mm. So 250 into 60. So load acting in Z direction 250 kilonewton, we are converting it as Newton. So 250 into 10 power 3 Newton divided by 60 into 250, we are getting the stress in Z direction as 16.66 Newton per mm square compressive. Okay, so after calculating stresses, now we are calculating strain along x-axis. So the formula is strain is equal to stress by Young's modulus. We know the Young's modulus is equal to stress by strain. So we are altering that formula, and we are getting the strain as stress by Young's modulus. Okay, so strain along x direction. So this is a cubic material. Okay, so stress by Young's modulus minus stress in y direction divided by Young's modulus into Poisson's ratio. That is this 1 by m. Similarly, minus sigma z by E into 1 by m. Okay, so this is the formula for calculating strain along x direction. So sigma x value we know 30. Okay, so 30 divided by 2 into 10 power minus 5 minus, similarly sigma y value and all we know, sigma y, sigma z and Poisson's ratio, Young's modulus, all values we know. So we are substituting this in this formula, and we are getting strain in x direction as 0.00015. Okay, so in the figure x direction we are applying a compressive force. Okay, so that is 300 kilonewton. Okay, so because of this compressive force, the material will shrink. Okay, it will shrink like this way. Okay, similarly in this portion also the shrinkage will appear. So there is a reduce in volume. Okay, so that only we are putting minus sign. Okay, so we are getting a strain in x direction as minus 0.00015. Okay, so because of this strain, so there is a decrease in dimension. Okay, so strain is equal to change in dimension by original dimension delta d by d. So we know strain and original dimension, so we can calculate the change in dimensions. Change in dimension is equal to Ex into d. So Ex value we know 0.00015 into 60. So we are getting delta d as minus 0.009 mm. So minus value denotes there is a decrease in dimension. Okay, so after calculating strain along x-axis, now we are calculating strain along y-axis. The same formula. Okay, Ey is equal to here sigma y by E minus sigma x by me minus sigma z by me. Okay, so m is nothing but 1 by m is nothing but Poisson's ratio. So we know all the values sigma y, sigma z, E, m and all. So we are substituting all the values, and we are getting Ey as 0.0000153. Okay, so here we are getting the strain as a positive one. Okay, so because of that we are getting increase in dimension. So strain is equal to change in dimension by original dimension. So change in dimension is equal to strain into original dimension 0.00153 into 250. We are getting the change in dimension as 0.0382 mm. Okay, so in y direction we are getting increase in dimension. So in y direction we are applying a tensile force 40 kilonewton in both faces, top and bottom faces. So tensile force automatically there will be an increase in length. Okay, so increase in dimension is occurring, that is 0.0382 mm. After that we are calculating strain along z axis. Okay, so strain along z axis, the formula Ez is equal to sigma z by E minus sigma x by me minus sigma y by me. Okay, so we are substituting sigma x, y, z and values and all, and we are getting strain in z direction as 0.4063. Okay, here the strain is positive one, so there is an increase in dimension. We are getting the change in dimension as 0.0025 m. Actually this value is minus, but here we are mentioning it as positive. Why means in x direction we are applying a compressive force of 300 kilonewton. In z direction we are applying compressive force of 250 kilonewton. Okay, so but in x direction the maximum force 300 kilonewton is acting. So in x direction we are getting negative strain, but in z direction we are applying a minimum force of compressive, that is 250 kilonewton. So Because of this force, we will not get negative strain. Okay, so only we are putting as a positive value, and we are getting an increase in dimension. Okay, so after calculating strain in x direction, y, z direction and all, we are calculating volumetric strain. So volumetric strain is equal to total volumetric strain is equal to strain in x direction plus strain in y direction plus strain in z direction, and we are substituting those values, and we are getting the volumetric strain as 0.4066. Okay, so therefore change in volume is equal to change in volume, EV is equal to EV is equal to delta V by V. So we know this formula. So in this formula we have to calculate delta V. So delta V is nothing but change in volume. So change in volume delta V is equal to EV into V. EV is nothing but volumetric strain. Okay, so we know all these values and substituting these values, and we are getting the change in volume as 39.66 mm3. Okay, so the result is change in dimension parallel to x-axis is 0.009 mm. Similarly, change in dimension in y-axis 0.0382 mm. In z-axis 0.0025 mm. So change in volume delta V is equal to 39.6 mm3. Okay, so this is the last topic in 4th unit. So your 4th unit is